case 14 and case 15 involve path distribution model. Okay, while case 12 and case 13, as we proceed before, we can see that there are involved continuous distribution process. So for case 14, okay, case 14 involve path distribution, instantaneous point source at height h above ground level. So it involves a coordinate system on ground move with path. Okay, in case 14, it involves coordinate system on ground and it moves with path. For this case, the center of the path is found at x equal to ut. Okay, we try to calculate the concentration at the center of the path. Okay, at the center of the path, with the average concentration is given by this equation. Okay, remember this equation also will be used in case 15. Okay, however, there are some modification on that equation. So for this case 14, this is the equation where the time dependence is achieved through the dispersion coefficient. Okay, if wind is absent, u is equal to 0. Equation 54 will not predict the correct result. Okay, because this equation 54 involve the inclusion of ut. Alright, okay, x is equal to ut. So if u is 0, equation 54 will not predict the correct result. So at the ground level, okay, there is no elevation, z equal to 0. The concentration is computed using this equation. So this is the equation, okay, to calculate the center line. Okay, concentration along the ground at the center line. Okay, this is the equation. So you have your previous equation. Okay, this is the concentration at ground level. This is the concentration at the ground level at the center line. Okay, this is at the center line. Okay, this is another equation if you want to calculate the total integrated dose at ground level. Okay, so as far as you are concerned with the concentration, should be okay to use this equation. Okay, the first one is the concentration at ground level, and another one is the concentration along the ground at the center line. Okay, so this is the equation for case 14. Okay, where the coordinate is moving with path. Okay, the coordinate system on the ground move with path. Okay, so we look at the case 15. Okay, case 15 also involve path distribution model. Okay, however, even though it's an instantaneous point source at height h above ground level, the coordinate system fixed on ground at release point. Okay, so there is a difference between case 14 and case 15 at the coordinate system. Okay, one is moving around with the release point, with the path, while another one is fixed at ground at the release point. So for this case, the result is obtained using a transformation of coordinate similar to the transformation used for case 7. Okay, so case 15 just using the transformation used in case 7. However, okay, there is an inclusion, okay, from previous case 14 punya equation. Okay, case 14 equation, path equation with moving coordinate system times this term. Okay, so this term will fix the coordinate system on ground. Okay, so you have one question, okay, for concentration. Okay, so this is HR. So what is effective height actually? Okay, effective height, okay, or effective stack height is the inclusion of physical stack height. Okay, this is the physical one, physical stack height, plus your plumb rise. Okay, this is your plumb rise. So your effective height is the inclusion or the summation of h plus delta h. Okay, small h plus delta h. So this is the effective stack height. Okay, if you want to calculate the concentration. Alright. Okay, we will see one example. Okay, how to use this equation. Alright. Okay. This is example how to calculate the distribution or gas distribution model. Okay, on overcast day, a stack with effective height of 60 meters. So it already gives you the effective height of the source. Okay, the effective height of 60 meters is releasing sulfur dioxide at the rate of 80 grams per second. The wind speed is 6 meters per second. So you need to determine A, the mean concentration of sulfur oxide, okay, sulfur dioxide on ground 500 meters downwind. B, the mean concentration on the ground 500 meters downwind and 50 meters crosswind. Okay, so this is the coordinate. Okay, you try to determine the concentration at this coordinate. Okay, on the ground, so means Z is 0. Okay, 500 meters downwind and 50 meters crosswind. And see the location and value of the maximum mean concentration on ground level directly downwind. So all are ground level. Okay, on the ground. A, B, and C is on the ground. So we look for the solution, how we can determine all the needed equation. Okay. So this is a container release. Okay, a stack with 80 high is releasing sulfur at the rate of 80 grams per second. So it includes, okay, this is a continuous release. The ground concentration directly downwind. So we use the equation. Okay. The question is which equation? So from table 5.1, the stability class is D. Okay, based on the stability classes. Okay. Okay, if you look for the stability class, is in class D based on the wind speed and the condition. So you have your stability class is D. So the dispersion coefficient is up to you. Either you want to use a figure or using a table. So we try to calculate using a table. Okay, sigma y and sigma z. Since sigma y is also equal to sigma x. Okay, so we have sigma y is 39 meter and sigma z is 22.7 meters. Alright, so where you put your x, okay, this is your x, 500 meters, okay, downwind. So this is your coordinate, okay, your x. So you have your sigma y, you have your sigma z. Then substitute into equation 5.51. Okay, you have your sigma z, sigma y, okay, sigma y, sigma z. Then you have your HR. Okay, this is your releasing rate, 80 grams per second. Your pi, 3.14. Sigma y, 339. Sigma z, 22.7. And then your wind speed, okay, U, 6 meter per second. Exponent, okay, -1/2. Effective height, HR, divided by sigma z and square. Okay, so you got your concentration at 500 meter downwind. Okay, so this is your concentration at that location. Okay, so what is the answer for question B? Okay, so you want to try you try to determine the mean concentration 50 meter crosswind. Okay, so your crosswind is, remember, y coordinate 50. Okay, so you got, okay, you put into equation, okay, you put into the equation setting y equal to 50, and then you got your answer. Okay, directly you can configure your answer. And see the location of the maximum concentration. Okay, remember the maximum, we try to work backward. Okay, try to find delta z first. Okay, using your effective height divided by square root of 2, you got your delta z. Then you use equation 5.52. Okay, try to find the concentration max. C max is equal to 2qm over epsilon pi u hr squared, okay, sigma z, sigma y, okay, the equation in previous video, okay, equation 5.52. Okay, you have your D stability, delta z has a value of 1200 downwind. So from figure 5.10, for D stability, delta z has the value of 1200, okay. So from figure 510 or table 52, you can figure your delta y, okay, delta y. So your delta y is equal to 88 meter, okay. Your delta z is 42.4, delta y is no, delta sigma, okay, sigma, okay, I'm sorry, okay, sigma z is 42.4, so sigma y is equal to 88. So put back into your equation, okay, for Cmax, okay, concentration maximum, then you got your answer is 4.18 times 10 to the power of negative 4. Alright, okay, so this is how you can calculate or use the information in every situation and put it into the equation based on your case study, okay. Even though if you can calculate using your case study, or if you don't know how to use what type or which case are you referring for, just use the basic equation first, then eliminate which situation or which condition that you can eliminate. Alright, okay, for further information you can look into example 5.2 and 5.3 in our textbook.